In this video, we're going to continue our discussion of redox reactions by talking about oxidation numbers, a system used to identify the current oxidation state of a substance and how those states change during a redox reaction. To go over a list of the learning objectives in the video itself, we'll start with a question of what oxidation numbers are. We'll have an official definition. You're then going to be responsible for assigning oxidations to individual numbers, similar to the way that they're assigned to these elements and substances down here. It might seem complex, but at the end of the day, it boils down to a simple set of rules that we can follow. And last but not least, we'll take some time to practice those rules. So oxidation numbers are an accounting system used to identify the current level of oxidation that an atom is in, or its oxidation state. It's important to note that oxidation numbers themselves don't necessarily reflect an actual physical measured characteristic of an atom, but again, they're more of an accounting system, a way for keeping track of how ions or atoms change their oxidation state through the course of a reaction. It's a system we use as chemists to wrap our heads around what's happening inside the flask. Sometimes these oxidation numbers or oxidation states are very similar to charge, but as I've already talked about, not every single element has a charge associated with it, but yet all elements need to have an oxidation state. So these can be assigned then, an oxidation state system can be assigned to any atom even if it has a charge or not. It is used to determine if or how much an element is oxidized or reduced in a chemical reaction. Like I said, it's an accounting system. We see the oxidation state before the reaction and afterwards, and we get an idea of how much change has occurred, which eventually will be used as a tool for balancing the reactions. The last and best news here is that it can be determined, oxidation states can be determined with a simple set of rules. Once you wrap your head around the rules and practice them a little bit, you'll find that assigning oxidation numbers for a particular element is a relatively simple task. Before we dive into the actual oxidation rules themselves, I just wanted to show you very quickly a kind of a list, a picture we saw earlier in the video of different elements and the oxidation states that they've been assigned. For example, we can look over here at carbon dioxide CO2. We can see that the oxidation state assigned to the oxygen atoms here is -2, and the oxidation state assigned to the carbon is +4. Just like we dealt with charges earlier in the year, these -2s and +4s, again, are reflections of the current state that this particular atom is in. And as you change the formulas and change the compounds, we see these oxidation numbers change. Again, your job in this video is to learn where these numbers actually came from and be able to assign oxidation numbers of your own. The real meat of the discussion then is actually determining the oxidation numbers of any particular element, and as the name here implies, this is all determined by a simple set of rules. Your job is to get these rules written down and then be able to apply them to any element that we come across in a chemical reaction. Conversely, if you look quickly on the internet, you'll find a lot of websites that have either documents or images that you can download that have these rules on them. The rules vary from place to place, but the idea behind them stays relatively the same. Any set of rules for determining oxidation numbers should be adequate for what we're about to do. We're going to go through the rules one at a time, starting with rule number 1. Atoms in the elemental form always have an oxidation number of 0. When I say elemental form, I'm basically talking at the atoms with no charge. So if I have a block of copper metal, that is copper the element, not copper the ion, that copper has an oxidation number of 0. Rule number 2, for monoatomic ions, ions made up of only one type of atom, the oxidation number is same as the ion's charge. So oxidation number and charge in this scenario are the same thing. This is how we were able to assign oxidation numbers in the previous video, despite not having had a chance to talk about what they meant. For polyatomic ions, ions made up of multiple atoms, the sum of all oxidation numbers in the ion must add up to the charge of the ion itself. So for example, in the carbonate ion, CO3 with a charge of -2, we'll learn later that our oxygens always have an oxidation state of -2. 3 of those gives me a total of -6. That must mean the carbon is +4, so that the +4 and then -6 adds up to -2, which is the net charge of the polyatomic ion. So by knowing the charge of one of the atoms in the ion, it allows us to not the charge. Now by knowing the oxidation state, it allows us to determine the oxidation state of the other atom. Next rule in the process is probably one that you won't find too surprising. The sum of all oxidation numbers in an entire compound must add up to zero. Just like charges had to add up to zero with ionic compounds, oxidation numbers have to add up to zero as well. Again, we can use similar mathematics from the previous step in order to calculate the oxidation number of unknown elements by comparing it to known elements and finding what is needed so that they add up to zero. Last but not least, nonmetals typically have a negative oxidation number. This isn't super duper helpful, but what we do get out of this is some oxidation numbers that we can assume. For example, oxygen typically has an oxidation number of -2, hydrogen typically has an oxidation number of +1, and all the halogens typically have an oxidation number of -1. This is going to be fluorine, iodine, chlorine, and bromine, but this is only when they are monoatomic ions. When these elements show up in polyatomic ions, that's when they have the other oxidation states that are listed on your periodic table. But when they are monoatomic ions, we're going to assume the charge is -1. So what I have for you right here is a bunch of compounds, various ionic and covalent substances. Using the rules we just came up with before, you should be able to take a moment, pause the video, and assign oxidation numbers to each element in each of these individual compounds. In a few minutes, I'm going to go over the answers for each of these, and then obviously we'll practice more of this in class. So really quickly, what I was able to write down here is all the answers for each of the oxidation numbers for each of these substances. Very quickly, just to go over a couple of them, these guys are both monoatomic ions, so the charges of the ions become also their oxidation numbers. Here we have a polyatomic ion. Hydrogen we said is typically +1. Oxygen we know to be -2. There's 3 of them for a total of a -6 charge. If the nitrate ion, NO3, has a charge of -1, that must mean the nitrogen is +5, so that the +5 and the -6 adds up to -1. Likewise, +5, -6, and +1 adds up to 0, which is the oxidation number they all have to add up to for whole compounds. CO2 we already saw. K3PO4, if each oxygen has a charge of -2, the total negative charge here is going to be -8. I actually made a mistake up here. If the PO4 ion with a -3 charge, if each one of these -8, that means the phosphorus must be +5, so that the +5 and the -8 add up to a net charge of -3. Potassium is simply a polyatomic ion, therefore it gets a charge of +1. NCl3 works in a similar way to carbon dioxide, and last but not, HClO4 works in a similar way to the K3PO4. Again, -8 charge here, meaning the chlorine has to be +7, so that when it's added to the +1, again, everything adds up to 0. If you're having trouble with these, if you're struggling, it is simply a matter of practice. The more and more times you take time to assign oxidation numbers, the easier and easier you're going to find this process to be. And that brings us to the end of our video. First, you should be able to describe what an oxidation number actually is. Again, it's an accounting system for keeping track of the degree of oxidation of an element and how that changes during a chemical reaction. And secondly, you should be able to determine the oxidation number of any element in any substance simply by using the set of rules we established here today. As always in class, I'd be happy to field questions and take the time to do some practice problems until everyone feels a little more comfortable with this particular topic.